Analysis of variance, aka ANOVA. Oh yeah, that's where we want to compare means from two or more populations. So in your Management Science 103, in the very beginning of Management Science 312, we compared means to a certain value. We didn't do so much with the means to each other. Now we fix that problem. So now analysis of variance comparison of means from two or more populations. There are many different flavors of ANOVA. We're going to deal with single factor ANOVA. There's two factor ANOVA, three factor ANOVA, and it goes on and on. We won't cover this topic, but an important sort of next step after ANOVA. So ANOVA, we compare the two means. Are they different? Are they not different? And then if we have two or more, if we have three, we want to know who's different. Okay, great. You got three means. You got four means. One of them's different. Awesome. Which freaking one is different? So that's where we start to get into paired comparison. Unfortunately, we don't have enough time to do it, but Bonferroni, Cheffe method, and there's a couple of others that you can take a look at. They're not too hard. They build upon the existing test structure that we already know, but they just make a little bit of adjustments to alpha to reflect changes there. So pictorially, we've got our one-way ANOVA. We have a series of populations. We have a series of means in those populations. And are they the same or are they different? And there's a nice little picture there. Okay. Now, the way it works is we are going to compare the variability within a group, right? It's just the natural random variability that exists within a group. And we're going to compare that variability to the variability between groups, right? The thinking being that if the variability, just the random, changes that go on within a group, if they're about the same as the random variability as we go from group to group, and there's probably no difference between those groups. But if we go from group to group and that variability is big compared to the variability within a group, then that is telling us, whoa, maybe there is a difference in these means. Okay. And we're going to revisit a good old friend of ours, the F statistic. Right, so we're very aware of the F statistic from our regression experience. Going to use that here as well, right? Because when we did it with regression, we were just comparing variability there as well. F statistic, awesome tool when we're talking about this variability issue. Okay. So just a couple of notation that we need to fixate on a little bit. We have what's called the response variable. Okay, we had the response variable in regression as well. We use it the same. Okay, same quantitative variable. It's a measurement. It's essentially our y. But sometimes for mysterious reasons, it can go by different letters. Okay, so it's not as there's not a hard, big, fast tradition as to it's always a y like it is with a regression or a line. Okay, so some examples that we may be trying to measure compensation levels, production time, job satisfaction, output, sales, revenues, stress levels, okay, and other performance measures. Okay, the next thing we have in our model is what we call a factor, a categorical variable. And this factor we use to explain differences in this variability in the response variable. So we had one example, I think a little earlier, where we had job classification and we looked at income. And we noticed that job classification for three different jobs had different earnings levels, different compensation levels. So that would be an example. Managerial classification made a different amount than the professional classification, which made different amount than administrative classification. So that would be our factor. Now, instead of setting up a whole series of dummy variables, which can get pretty crazy pretty quick, now we just have the one categorical variable, and we have treatments or levels within that categorical variable, right? So it functions very similarly to a dummy variable, except now we just need one of them, and then the different levels within that factor, that categorical variable, are already incorporated into the ANOVA. So very nice that way when categorical variables are a major component of what explains what's going on with that response or Y variable. So that's really, really, really cool. Okay, so we have our single factor experiment. Okay, one qualitative factor. It doesn't have to be that way. Okay, we can have actually more than one response variables. Behind scenes math gets to be complicated, and organizationally from a statistician's point of view, from experimental design point of view, it can get tricky as well. Computationally, it's actually very straightforward with modern stats packages. Okay. All right, so we have a single factor, multiple levels within that factor. But again, you could have two-factor ANOVA, three-factor ANOVA, and so on. Randomized block design, it can really be very, very flexible in how we use ANOVA. For now, we're just going to get the basics so we get the idea straight. So we have our model, okay, and we have our little yi, two subscripts, our response variables, right? We have our mu. Now that's sort of like an average, like we've known mu to be so far, but it's an average common to all. It's kind of like a base starting point. And then we have the Greek letter tau. And the Greek letter tau is one of my favorites because for these uncertain COVID-19 pandemic times, you just think of the word tau and you could just feel the stress going away. Just say it with me. Tau. Look at that. You could feel, oh my gosh, what? Oh, I don't care about COVID-19 anymore. Oh, tau. And tau is for treatment level. And then, of course, we have error. There's always error. Always those things that we just don't know why it's that way, just unexplained. Okay. So yi, actual response, the actual measurements. Okay, so for instance, if we're looking at hourly work, hourly wage, we're looking at an hourly worker in a given, let's say, province. Okay, so province would be our factor in that particular respect. Mu would be overall average across all groups combined. So just sort of like that, the average, right? There we go, got the average. Average across all groups. And then the treatment level would be, let's say, the province that you're in. Right? And so we can kind of see, okay, if you're in Alberta workers tend to have a higher hourly wage than workers in other parts of the country. So this treatment effect for Alberta workers would be adjusted, would be positive. Right? Off in the Maritimes and Quebec, less than average. Okay. Now, if there was no difference, if there's no difference across BC to Alberta to Quebec to the Maritimes to Ontario to Manitoba and so on, then we would see that those means for each one of those provinces would be equally variable than means within each mean hourly wages within each province. Okay, so now what happens is we have an error term, right? Because we're saying averages here. Right? The average Alberta worker makes more than the average Canadian worker. But that does, now we start talking about the random error. That refers to a specific worker or perhaps even a specific industry if the model is set up that way, right? So an individual worker may be earning a little higher or lower for a whole host of obvious and controversial reasons. Okay? Maybe you're a better negotiator and you happen to be a little bit above the average. Okay, so a couple of things that go on. So we missing factors, right? We stole that error term, missing variables in the model, still like with regression, still important here, okay? Could be that when you look at Alberta and earning more than typical Canadian province, it could be the occupations that Albertans work are different than the occupations that Albertans or that Canadians work or Ontarians work or Quebecers work and so on, okay? So that could be a factor that's important, but it's not dressed in there. It's just covered by this overall province thing, okay? And then, of course, pure random error. God bless this free market system. You have, if you're able to negotiate a better wage, go for it. That option is always up to you. Okay, so we have some assumptions, and two big assumptions, and we had these assumptions with regression as well. The y variable, the response variable, and the error term are normally distributed. Yeah, so we carry over from our regression days. The new one here, and we sort of had it. We had it with the whole homoscedasticity, heteroscedasticity issue in regression, and we sort of have it here too as well in ANOVA. Okay, and that is that the variance for the response variable same across all treatment levels. So the variability of, let's say, wages in BC, same as the variability of wages in Alberta, same as the variability of wages in Ontario, and on and on and on. Okay, that's a very important assumption. That's an assumption we need to check. Not the end of the world if they're not equal, just that this is a method we can't use in that particular case, or shouldn't use in that particular case. But there's other choices. Okay, so we got to check to make sure that the variances are equal. Very simple thing to do. Now, it gets tricky as to what is equal, right? They're not all going to be exactly the same. That's silly, right? We know that's not the case. Right? It's going to be a little bit of fluctuation. So we sort of have a quick and easy rule of thumb that we can use to see if those variances are equal enough. Okay, and the quickest way to do this is just take we get our output and we look at the largest variance divided by the smallest variance. If that's less than or equal to 3, they're all going to be equal enough. Or alternatively, largest standard deviation divided by the smallest standard deviation less than or equal to 2, they're equal enough. And behind the scenes is a little bit of a testing methodology, and this sort of follows that in more of a rule of thumb rather than a formal testing kind of way of thinking. Okay, so very important, right? It's one of our things that we're going to verify when we do our ANOVA tests. Is we're going to run this little check to make sure everything is good, and we'll do that in step number 3. Okay, so analysis of variance procedure. What the heck are we going on now? I'm going to go through this a little bit. And it's not super important that you get the details. We really want to get the flavor for what is going on here. Okay, so we take random samples of the observation, always assuming that there's random samples here. That's standard stuff, nothing new there, right? We sample each group, so each level in the factor. The distribution for each group is assumed to be normal. The group sizes do not have to be the same, though. Right? We can sample a different number of folks from Alberta than we do from BC. So we don't have to be all the same. And then, of course, we categorize those people. And so what we're saying is, or what we're looking at it is, we got all these groups, right? Group 1, Group 2, Group 3, and so on. And they all have their mean. And their means are whatever their means happen to be. And then they have a certain variance. Now, the variances has got to be the same across all groups, even though means do not have to be. Right? And the sample sizes do not have to be. Right? So a lot of things can be different, but there's one thing that we really need to be sort of or close enough to being the same. And so we run our samples, we get our results, and we have some sample variances. Clearly, we don't know the population variance without actually sampling everybody, and we don't know the population mean without sampling everybody, but we do have a series of sample means that we will compare. So our hypothesis, step number 1, HO, every single one of those means is the same. They don't have to be equal to anything in particular. Notice that. Don't have to be equal to anything other than they're equal to each other. And then HA, at least one of those is different. One of these things is not like the other. One of these things just doesn't belong. Okay, so one of those means. Again, you got to follow up with the multiple comparison of means, Bonferroni or whatever, to see who is different. But at least we'll know that somebody's different and that, further work needs to go. Step number 2 is as step number 2 always is. Alpha equals to whatever, right? And we got the old twin pushes of balancing of type 1 and type 2 error. Step 3, our test statistic. It is an F distribution, and we know from our regression experience that that F statistic has 2 different numbers telling us what its degrees of freedom are, right? Same thing with the regression, right? We saw that there before. In this case, the F distribution, the numerator degrees of freedom is k minus 1. That is the number of factors minus 1, right? Very similar in kind of thinking is what we had when we looked at regression, numerator degrees of freedom. And the denominator degrees of freedom is the total n, total sample size, minus the number of levels in your factor. Okay. So we have all these samples, and we got all these results, and so on, and we're looking at the variability within each one of those groups. Right, so we have the variability within one of those groups, and that's what we're going to compare. Right, we're going to look and see how much is the means different as we go from group to group to group, and how does that compare with the amount of variability we expect to see within a group. Right, the variability within a group, that's just that random stuff, or what we consider to be random stuff. Okay, so now I'm just going to break down that F statistic formula, same way as we did in regression. It's more for background, just so we kind of have a gut or an intuitive sense for where the numbers are coming from. So we have the numerator, mean squared of the treatment effects, right? And we look at the sum of squares of those treatments minus, again, the degrees of freedom related to that, right? And we start to see, oh, I see where that F statistic's coming from, because that looks like that must be chi-squared distributed, right? Oh, look, that's in the numerator. We're dividing something that's variable or sum of squares or something and dividing it by some magical number. That magical number is the degrees of freedom for the numerator, right? And in this case, it's k minus 1, k being the number of levels in the factor. And then we compare that to the denominator. Holy cow, look at that. Sum of squares errors divided by some mysterious number. What is that mysterious number? The degrees of freedom for the denominator, right? Total n minus the number of levels in the factor. So same kind of idea, same structure. It's looking at very similar stuff as what we had in the regression case. Okay, complicated stuff. You can look at that on your own, just in case you need to break down the numbers of where do those come from. And you can kind of see just superficially without getting too carried away, that here we are. Anytime we subtract something, that's a way of comparing. And we're comparing the means of each one of the levels in the factor to the overall mean to see if it's much different. Okay, and so that's where we get what's driving our numerator. We compare that to just the random error within these levels, right? Comparing individual observations to each of their respective means. Okay, so there we're getting a sense for the variability within a factor there. And if the variability we see as we go from factor to factor is about the same as the variability we see within a given factor, right, we're going to expect a very, very small F statistic. Right? That's just intuitively what we're looking at and what we're thinking is happening. So this is a nice little table. It breaks it down. Most outputs for most programs follow this structure. They add, of course, their own little tweak to it. And so we've got this breakdown. Okay, so one moment. Those of you who know me, been in person, I got to take the celebratory toast of a little bit of Pepsi here. Caffeine boost for the end. Okay, so we have this table and the standard breakdown. Everything is building up to the F statistic and ultimately to the p-value related to the F statistic, right? And that's an ANOVA. And we remember from our regression experience, holy cow, when we looked at that Excel output, that whole build up to the F-stat, what the heck was it called? It was an ANOVA table. Oh, wow. Could they be related? Absolutely they are. Okay, you can kind of see the same flavor, same general structure working. Our whole goal is we're building up the components to calculate that F statistic, use that F statistic to find its p-value, and use that p-value to make decisions as to whether those means are indeed the same or at least one of those means is not like the others. Okay, so we have our F statistic, and again, just to summarize it up, step 3, that's the F statistic. Not forgetting the degrees of freedom. Okay, a couple of nice things about the F statistic is that we're going to reject H naught when that F statistic becomes large. Remember, we're comparing variability as we go from factor to factor to just the natural random variability within a factor, right? And if that is that's a lot different, that means, hey, those means are quite different from each other. One of them must be not like the others. And so large F statistic, small F statistic, just the reverse. Test is always upper-tailed like we've had for the regression case. That's really awesome. Not keeps our complicated our complexity down. If the expected value of F is 1, HO is indeed true. Now, HO is true. Now notice, oh, hey, Alan, whoa. You never say HO is true. Well, that's about as close to saying HO is true and being pretty safe about it as you can possibly get. Right? Don't anticipate that happening too terribly often, if ever at all. Okay? And of course, when the F statistic becomes large, guess what? One of those means it's not like the other. So here's our decision. Are the means all the same, equal to some common mean, right? The mu at the very end, it just means, hey, it's just, they're all the same. You don't need to worry about that too much. If you just say mu1 equals mu2 equals mu4 equals mu3 equals mu4 and so on, depending on how many mu's you have, you're fine. Okay. Reject H naught as in the same way, right? The rule is the same. Step 5 is the same. Step 4, we have the p-value. P-value is right, nicely placed on the output. Everything else is the same. Right? Follow the same structure. Okay. Now I'm going to do this example in another clip. So stay tuned. More ANOVA is coming right up after these commercial breaks.